A couple of words about myself. I've 6 months ago I've started a new job at Scraping Hub, and at Scraping Hub what we do is we do web scraping. So about myself, I've been coding Python for, I don't know, 12, 13 years, and I'm currently the team lead data science for Scraping Hub. So we have a team of, depending on how you count it, 5 to 10 people who work with data science in Scraping Hub. And so a lot of the stuff that we do is natural language processing, automating web crawling, and automated data extraction. And so the tools that we use a lot is Spark, Dask, TensorFlow, sklearn, and things like that. So at Scraping Hub, we do web scraping. So people will, our companies will contact us and say, we'd like to find out about what's going on the internet. And we scrape about 4 billion web pages per month. So there's a certain element of scale involved and performance that's required. And then in terms of what people want with internet information, people are looking, or companies are looking for product information. They want to know about product reviews, who's talking badly about something, what's their sentiment about certain things, what are competitors doing. And also recently for a while we've done some work on the dark web, so to look for criminal activity there and try to find patterns that Google may not have indexed at the moment. So as the premise for today's talk, it's really a lot about, it's really quite easy to get big data sets. So whether you contact a company like Scraping Hub, or whether you write something yourself with Scrapy or another tool, it's quite easy to scrape 1 million data sets, or 10 million, or 100 million. But the problem is the value often lies in the connection of the data sets. So if you scrape one website and another, they will have the same entities, but you need to merge them. And that's kind of a big challenge, because often, unlike in a SQL world, or the world that most of us are probably used to, there's often no unique identifiers. So there's no, often, for example, if you're talking about products, the UPC number, so there's a universal product identifier, but that will often not be shown by websites because they don't really want to enable that kind of comparison. And so then the question is, if I have two data sets that we know share some entities between them, but they have no unique identifiers, how do I match them? How do I join them? How do I get the value out of that knowledge that connects the two? And so the overall theme is probabilistic record matching. So how do I make an educated guess that two things are the same, even if they're not identical? So as a very simplistic example, this could be what it looks like. So you have 3 entities or 3 rows in 3 different data sets, and they all refer to the same person in this case. So you have different ways of the person being represented, different formats for the birth to be shown, and different address or geolocation ways that is expressed. And so that's the basic problem definition. We have the situation that we have databases of products, or people, or companies, or hotels, and things like that. And what we want to do is to find likely matching records. So maybe we want to find within the same database entities that are duplicated. So that happens quite a lot. If you talk with Facebook or other databases like that, there's a lot of duplication going on. But even more importantly, if you have 2 databases, how do you match them together? And I have an example here. So we could have 2 company addresses, and one says Lookwood Limited Ltd, then it has an address and a phone number, and then the other one refers to the same entity, but if we do just string comparison, then we will miss this one, because the address is much longer in the second case, the phone number looks pretty much completely different, and even the company name is not the same. Are there any questions about kind of what we're trying to do? Is there anything that you'd like to ask? So I'd invite you to just jump in if you do have any questions. Okay. So what are a few challenges? So if we have really small data sets, then this isn't actually, I mean, it's probably still hard, but it's not a huge problem. The problem comes when our data becomes a little bit bigger. So for example, if we have two databases, each with 1 million entries, then if we want to do pairwise comparison of each entry to each other entry, that's 1 trillion comparisons. And, you know, like 1 million is not really a big database. So if we scrape data, or if we have data that's publicly available, it could be hundreds of millions of entries. So clearly doing pairwise comparisons is not feasible. The second point is that what we want to do at the end is to build a graph that says how similar are different entities to other entities, and then we want to find connected components in that graph so that we can find what are clusters that are close together and where is there not such a good discrimination between them. And also connected components and community detection algorithms, they don't scale particularly well. So depending on what we choose, and there's been a lot of progress in this field, but it could be n cubed or n squared. So in many cases, more than a few thousand entities in that graph is going to be a computational problem. And then the third point, and I'm going to stay quite a bit on that today, is that the same entity can be represented in different ways, and different entities can have similar representations to each other. So we need to find a good way. How can we find entity aliases, so when the same entity has multiple names, and how can we deal with entities that look similar but aren't? And then the fourth one is not really a challenge, but it's more a reminder that when we compare fields, we need to treat them differently. So we need to treat, or in theory, we could treat everything as a string, but that's probably not what that won't give us the best results. So basically, if we have a phone number or an address, or a person's name or a company name, we want to do slightly different things to those fields to get the best results out of it. So in terms of what kind of field types one might encounter, this is just an example of a couple of field types that we deal with on a very regular basis. So it could be a person's name, it could be a company name, a university, a product name, a brand, could be a price, a lens shift. It could be an address, a geolocation. So we deal a lot with these, but there's also other very interesting fields where people are looking for similar images, and then you can use deep learning, or you can use perceptive hashing and things like that. But basically, we have different types of fields, and we need to treat them slightly differently. So what would be an example of what we're talking about? So we can have typos, and so a lot of data is still entered by humans. So whether it's people on websites that just type in things, or object character, OCR, character recognition, so that there can still be typos. So there could be white space, there could be uppercase, lowercase differences, or just simply some kind of typo. And then also the data can vary syntactically. So we can have the same value expressed different ways. And then if we just do a naive comparison for identity, then we won't catch these cases. And then, yeah, the world that we live in is quite complicated. So if you look there's so many ways of expressing the concept of Munich. So you can have it in English, you can have it in German, you can have it in German without the umlaut, you can have it in French, you can have the latitude, longitude, zip code. The people in Munich themselves, they have their own dialect, or you can have it in other languages. So all of these things potentially refer to the same thing, but they have very different string representations. And then also entity can be ambiguous, or actually in the real world they will be ambiguous. So for example, if we're talking about Munich, we could be talking about Munich City, we could be talking about Munich County, or we could be talking about Munich, North Dakota. So another thing to take care of is that the same entity can be expressed multiple ways, and multiple entities can be referred to the same way. So if we actually go to, let's see if this works. If we go to the disambiguation page on, that didn't work. Let's see if we can get this. Wow, that's very big. Wow, that's unhelpful. So this is the disambiguation page on Wikipedia. So there's a lot of things that could be.
Did the user share in the content? And then for the content itself, we just did some.
So coming to the next part. So there's actually really nice libraries available in Python that can help us with all of these things that I just discussed. I think the two libraries that I like the most are libpostal and Geonames. So what libpostal is, it's an open source library that was trained on a very large data set from OpenStreetMaps. So it's able to parse addresses and give them back to you in a normalized form. And the other database is Geonames, which is actually a really almost too large. Like it can be a challenge to deal with, but it gives you the ability to look up cities and different names. All these alternate names are available. It gives you the ability to find out the geolocation for a city, or to find the city by a given geolocation. Then in terms of parsing person names, there's a nice library called Probable People, which allows you to parse a person name and give it back in a standardized or in a normalized form. For dates, there's date parser and idle time. Date parser, you just give a string and it tells you what it is, whereas idle time takes that a little bit further and finds date references in longer texts. But both of these are nice. CleanCo is a nice library, and I'll give a quick demo or a quick example just after giving a quick overview. CleanCo is an interesting library for parsing company information. And one thing that we're working on at the moment at Scraping Hub is to leverage the information that's available in Wikipedia. So Wikipedia has redirects and it has disambiguation pages. So for example, for companies and for universities, it gives you many, many alternate names for the same entity, and that helps a lot to build a database. And then when we come to the actual deduplication or record matching, there's a couple of libraries. So there's the library called dedupe. It's a very cool library, and they recently also announced a commercial web service based on the library, but the library itself is open source. So that uses active learning. So it asks you, are these two the same? Are these two the same? Are these two the same? And by that it learns what similarity features should be employed and what weights should be employed. So that's a very cool library. And then there's a Java-based library actually based on top of Elasticsearch called Duke that allows you to do record matching in a very simple way, very easy way, albeit it doesn't scale to hundreds of millions of records. So it's probably a good solution to get started if you have around 1 million by 1 million, something like that. So I'll just go over and do a quick, let's see if we can make this work. That's very small. I don't know why this happens. If there's somebody in the room who can tell me why my screen always disappears, I'm open for thoughts. So, can you read that okay? So this is just a couple of things that we've come across in the past. So if you're looking into people names, then it can become very messy very quickly. Well, I think my favorite part is where people put their star sign in their name. So it's like Johannes lion, almond. That was unexpected. But there's many ways that people use names because of the culture of heritage or things they want to communicate. So people love putting titles in their names. So there's a whole study of prenominals and postnominals that mess up names in general. Then there's all kinds of European names for Asian people, maiden names. I like this one where it's like a Russian name and then a dash Campbell. So lots of, I think there's, I love that website where it says, what is it, 50 falsehoods programmer believe about names. Like, I'm totally culpable of that, even though I was aware of it, but there's just so many things that can happen. So if we take the library Probable People, then what we can do is we just give it a name and it will parse that name for us. So we'll say, Mr. George Gobluth II is Mr. is the prefix, given name, nickname, surname, and a suffix. So that's really quite nice. It has very much limitations because names are just so incredibly hard, but it's a really nice starting place, this Probable People library, to get to a normalized form of a name. And then another library that I really liked is this library called CleanCo, and you give it a company name, and it tells you the type of company, so it's a limited liability company, where it's most likely from, based on the legal form that it has, and then the cleaned up name down here. So I found actually in our use that the library itself was too slow because it was doing a lot of things that I didn't need at the time. But it has a really nice list of legal suffixes and prefixes. You know, every country has different legal forms and abbreviations for those. So we actually use those abbreviations to do the cleanup of company names. Then for date parser, probably not the most relevant example I have here, but in French, when you say 2 hours ago, then the date parser goes, oh, that's a relative date. But the same goes with if you have dates in French or Chinese or weird formats. It also detects the format. So, you know, date formatting is a science in itself. One library that I really enjoyed was SimString. So what SimString does is it indexes letter n-grams of strings, and then lets you look up similar strings. And unlike most other libraries that I've seen, it's actually really fast. So there's a couple of caveats. So it doesn't work well. Well, basically you can't parallelize it as it is, and it won't work somewhere beyond 10 million entries. But if you just have a couple of million strings and you want to find similar strings based on a threshold, it's actually a really good library. So you can see here, so it's just on a random machine. So you can insert 10 million strings in 1 minute, and you can query 1 million strings in 2 minutes. So it's actually a lot faster than a lot of other libraries. So here I've just taken a dictionary to do some testing, unit testing, and so I've added some numbers to the standard dictionary, and then I'd retrieve a misspelled form of esophagus. And so these are the results that I get back at a threshold of 0.35. So the threshold is a little bit tricky to come up with. But so you can see that it finds these, in a very, very fast manner, these similar strings. So that's a really nice tool to have. And then, as I mentioned, Pare Postal before, it's really an amazing library. And if you ever have to deal with addresses, please don't write it yourself, because I'm not sure which is worse, names or addresses, but they're definitely close to each other. So here you can't really see it, but you just give it a string where it says the book club, Leonard Street, Shoreditch, London, United Kingdom, and it will split this apart into house number, road, suburb, city, postcode, country, and then you can put it back together in a standardized form. So people will throw addresses at you, and you can turn those into at least standardized form, so that if the address makes sense and fits into libpostal's assumptions and model, then you can actually you could in theory even get identical strings from different input strings. And it also gives you the option to expand, to do different expansions. So here you can see it's Leonard ST, so that could be either Leonard Street or Leonard Saint. So clearly not a lot of context knowledge there, but it's actually a huge help when you deal with addresses. And then a beautiful library, or a beautiful data set is Geonames. So something that comes up a lot for us actually is the same city or the same country written in a different language. So where it says, instead of München, it says Munich or Munich, or I don't know how to say it in Chinese. But so it actually has a lot of alternate names. This is just a small selection, but where you can say, give me the alternate names for Munich, and it says, well, there's the Spanish Munich and the German Munich and the French Munich. And then also you can say, tell me what city this is, and this is the Chinese version of Munich, and so it will give you lots of things that I'm not showing here. It will give you the latitude, longitude, it will give you what countries it's in, how many inhabitants, what type of a city, whether it's a town or a village or a city or whatever it is. And then you can also do the same thing by looking up by latitude and longitude. So if you know, which actually happens quite frequently in web scraping, sometimes locations can be obfuscated. So where it just says it's roughly here somewhere, and you'd like to know what city is nearby there, or what region does this city or another. So in one set you have a region, and in another set you have a city, and now you want to find a correspondence between the two. And Geonames is really good for that. So you can actually look up by latitude and longitude and say, tell me what the nearest city is to these coordinates, and we'll say, oh, the nearest city to those coordinates is Munich. It's in Bavaria, it's in Germany, it has a population of 1.26 million, and then a lot of other information. So this can be really a lifesaver if you deal with, so in the combination of libpostal and Geonames, this is really amazing to get a normalization out of your data. So let's see if we can go back or not. Let's see. Okay. Where's my mouse? Okay. So these are a couple of tools that we use on a regular basis. For data exploration, there's a really cool tool from Google, which is called OpenRefine, which lets you load a data set into. You can explore the data set in the web browser, and it will do some clustering for you. It will do some analysis for you. So that's really useful. And then for connected components, there's actually a lot of libraries. We use iGraph and we use Spark to do our connected components. So I've given a bit more time to the standardization and normalization, because I think that's something very practical. So if you have a string and you don't know what to do with it, then these libraries, they can be really helpful. So what happens then at the end is, as I mentioned before, pairwise comparison doesn't really work, because it's just a quadratic explosion of pairs. So what we want to do is, first we want to standardize and normalize our fields. Second, we want to find a fingerprint function. for each field type, so that we can take the field and put it in some kind of a high-dimensional space so that we can do direct distance comparisons without comparing everything with everything. So basically, what we're doing is we want to hash something into n buckets, and if two things are in the same bucket, then they should be similar. So those would be candidates for comparison. And then so what we use for that is SimHash or MinHash or solutions for that, but it has to be different for each field type. So for strings, this is quite well established. So MinHash is a really good algorithm in that space. But then for numbers and dates and things like that, you may need to find a different algorithm that gives you similar items going into the same bucket. And then we can just take one bucket, look at all the ones in there, and put them in a graph and do a nearest neighbors, and do a community detection or connected components, and that will give you all the similar items based on the standardized, normalized, hashed buckets, and then it'll give you all the entities that relate to each other.